Can you hear me? Oh, okay, this works. Okay, hi, my name is Liana. That's Wally, he's my sidekick. I work on planning with uncertainty, and what I'm going to talk about today has to do with improving heuristics when it comes to problems with numeric uncertainty. Why do I think this is an important problem? Because there are plenty of cases where you have to either gather some resource or use up some resource, like level of battery, some samples of rock and soil from Mars, some cargo that you have to load up and move around. And there may be uncertainty on these numbers. There is some really nice prior work by Bergery et al. That made a nice planner called RTU, that stands for Resource and Time Uncertainty. That planner has then been extended by Coles to deal with numeric uncertainty better, but there is still one thing it doesn't do. It does not take uncertainty into account in the heuristic at all. So numeric uncertainty is modeled pretty straightforwardly as a Gaussian distribution over, for example, the amount of battery that you use up when you go from a place to another. But the heuristic only uses the median of that Gaussian distribution. It doesn't know anything about how much variance there is on it. And this is not great, and I'll give a short motivating example of why this is the case. So suppose we start with 50 units of battery. We move around a lot. We move around 8 times. So we should have about 10 battery left. But if all of those move actions had some uncertainty on them, we probably don't have exactly 10 battery left. Maybe we have 11, maybe we have 9.5, maybe we have 8. So at this point, we want to ask the heuristic, okay, how far is the goal now? And with the prior work, the heuristic will be perfectly happy to tell us, oh, it's just 1 step away. We have 10 battery. That's the median. We can totally use that 10 battery to do something very critical, like turn on the lasers. But that's probably not the case. Especially if it's a very critical thing, we want to be really certain that we have that 10 battery to use up. So we want to track the amount of variance that there is in the heuristic. The crucial thing is this bit here, the offset. So normally preconditions are of the form v greater than or equal to c. If we say that they are now v greater than or equal to c plus offset, what we've just done is we've made the preconditions a little bit more difficult to achieve. So when our heuristic goes on and expands the RPG using those types of preconditions, it's going to be a bit more cautious. It's not going to assume, yeah, we've always got the median, we're safe. It's going to give itself a little bit more space to accumulate some uncertainty and still be okay. So the way we compute this offset is fairly straightforward. We need 3 things. We need theta, which is an amount of confidence that we require from the problem. This is from prior work, and it's something that's specified when we begin. We need sigma, which is the square root of variance, and we are keeping track of the cumulative variance, so we have that. And we also need the cumulative distribution function, which for a Gaussian is that percentile under there, and the handy thing about Gaussians is that all of the math is implemented for you, so that's already in the library. We've got that too. So using that type of precondition in the RPG expansion and then later in the relaxed plan extraction, as I'm going to show in a second, the heuristic can do 2 very useful things now. It can check if the preconditions are achievable with that specified amount of confidence, theta, and it can also consider applying some variance-reducing actions, if they exist, in order to make some of those preconditions achievable with theta later on. So we found 2 cases of problems in which variance behaves in interesting ways. The first one is when variance can only ever accumulate, and we cannot get it down at all. And the second one is if we can do something about it, if we have a way to calibrate something, to remeasure something, to recharge the battery, to go back to the start and reset. So this is the first case. This is Wally trying to move around. He starts with 100 units of battery in a location, and he starts with 0 variance. That's sort of the start point of the problem. And as he moves along, every step of movement that he makes is adding, in this case, 1 unit of variance on top of each of those Gaussians. So you can see that they're getting wider and wider. And we need to be pretty cautious, right? Like Wally's being over there. So in this case of accumulating variance, the best we can do is look at these preconditions and always be checking, are they achievable with enough confidence given all of this accumulated variance? So that's kind of the best we can do. We can expand the RPG conservatively. But the next case is a bit more interesting, and it's actually quite a bit more common. Most problems have these. So if Wally has certain locations where he can sit down and he can bask in the sun and he can recharge his batteries, this is what happens. He shoots back up to 100 battery and back to 0 variance. So this recharge action has just reduced our variance back to 0. That doesn't have to always be the case. We can have actions that reduce variance by some amount, not necessarily reset it back to 0, but the theory still works in the same way. So if we're in this sort of case, where we are able to reduce variance, then we can make good use of these types of actions by asking, okay, if at some point in the future I have a precondition of this form and I want to achieve it with, say, 90% confidence, how much do I need to reduce offset by in order to achieve that? So that means that when deciding what actions to put in the relaxed plan, the heuristic can go, okay, I'm going to put the appropriate amount of variance-reducing actions in here in order to get that precondition to an achievable level at the time where it's relevant. So this is what happens in the RPG. The top RPG is just the prior work where the median is used, so variance is not taken into account at all. And it just says, first step is, sure, we can navigate from A to B. But you can see there that in the first step, we already have some amount of variance there. We have sigma squared 4. So with our extended version of the heuristic, it actually says, well, that's quite a bit of variance you've got there. We need to take it down before we can successfully navigate. So what it does is it includes a recharge action in the relaxed plan. Sorry. It includes a recharge action in the relaxed plan, and this takes the sigma squared value down to a lower bound of 0. So we can now use that lower bound of 0 to be more to be able to say that, yeah, at the next step, it's possible to have sigma square low enough in order to achieve the preconditions of navigation with a high enough level of confidence. Right, so these two different ways of looking at the problem have both worked quite well, and we've evaluated the metric RPG heuristic from prior work that used the median of the Gaussians with our version where we kept track of variance in the heuristic. And we saw pretty significant improvements in both nodes expanded and time taken. So this slide shows nodes expanded, but the scatter plots for time taken look basically identical. You can barely tell them apart. So same trend there. Everything under the bisect line is good. That means that we performed better than the prior work. In particular, those circled blue dots over there mean those were problems that were previously unsolvable with the prior work heuristic, and now we solved them, which is really great. A couple of words about the domain. So in the rover domain, we had uncertainty on battery, just like I showed in the examples throughout the slide. TPP stands for traveling purchaser problem, and in this domain, we had some uncertainty on the bulk amount of goods that we had to purchase and carry around. And in the AUV, autonomous underwater vehicle domain, there was some uncertainty on the amount of time that it took to solve various underwater tasks because of unknown water currents. AUB looks a bit funny because it's an oversubscription problem. So we plotted both the first three, the second, third, and fourth solutions. But in all cases, you can see an improvement. The improvement was sort of most visible in the fact that it found more solutions earlier than it normally would have. But anyway, overall, it's quite good. Okay, how long have I got? Again. Okay. So just a very quick word on why we didn't break anything. This is still a relaxation in both of those cases. So I'll quickly go back to the two variants. So in the first case, our heuristic is still a relaxation because if variance only ever accumulates, the problem only ever gets harder to solve. So when we evaluate the heuristic, we just grab the amount of variance we have in the state we are evaluating, that's guaranteed to be a relaxation, because it can only get worse from there. And in the second case, it is still a relaxation, because in that case we know that the relationship between variance and offset, while it's not a linear one, as you've seen over here, it's not linear, but it is monotonic. So we can count on that to know that it's still a relaxation. It's what we've done is okay. It's still a valid relaxed plan. Okay, so this went well. We've kept extending it. We've used the same mechanic to policy building approach. That just got published as a short paper in E5. And that's it. And if you're interested in policies, stay for the next talk. It's a really good talk on policies after me. Okay, that's it. Thank you.
Thank you very much. Any question? Yeah.
I'm just wondering, so you have different action types that consume battery, right? And what if they have different distributions with respect to uncertainty? How do you start combining these cumulatively?
If they're all Gaussians, it works. They sum up. So I've only showed the formula for one variable, but it generalizes immediately to weighted sum of variables. So if they're all Gaussians, it works fine. If they're not Gaussians, I'm working on it. I'm halfway through coding a way of using a distribution that's not a Gaussian. You can specify a combination of different probability distributions. So,
Not all variance producing actions are created equal. So if I'm destructing battery conditioning, that battery I have at some time should I construct not show I'm cautious. Or we have to consider a consistent set of responses to be maximally destructive battery and then variance and your battery state structure. What happens if I say I told you the work is going to be charged in 10 minutes, but I don't know what the battery discharge rate is?
That is more up to how the problem is specified. So we have had to make some assumptions and abstractions at the level of how we specified the actions. For example, in the PDDL, we had to sort of manually say every time we move, we increase variance by 1. We don't know if that's really 1. We hope it is. Later, we'll try and learn that amount. But so things like these are things that we've had to initially approximate to something reasonable, and then say, okay, next step is to actually try and learn from experience, something like what you said, what the rate of discharge is, or what the profile of the uncertainty looks like, because maybe it's not a Gaussian, but things like that are things that we are looking at learning in the future.
You showed an example where the precondition is the lower bound, right?
Mm-hmm.
What happens if you have both a lower and an upper bound? Like when an airplane lands, it means you have no more than 20% sure that it's tanking, obviously no less than 0.
So what we've done is whenever we've treated them separately, we've transformed all of our preconditions look like that now, because we've sort of swapped the ones, we've multiplied them by -1 to have like only one bound. So we haven't looked at problems in which those sort of conditions appear. I don't think it will break, but we do need to try. Thank you for pointing it out. Yes, thanks.
Okay, I think we need to move on. Let's thank the speaker again. Okay, so now Alberto Camacho will speak about paper named From Font to Robust Probabilistic Planning, Computing Compact Policies that Bypass Avoidable Dead Ends. By the way, I was asked to reduce the volume of the microphone, but I don't know how to do that. So if someone can help me. To reduce a bit the volume of the microphone.
Thank you. Thanks, Mark. So, in today's talk, I will present joint work with Christian News and Sheila McIlraith in probabilistic planning. And as some of you may know, there exist several formulations for probabilistic planning, such as max-prob or stochastic shortest path problems. All of them have that particularity that the effects of the actions are stochastic, right? So, but all these different formulations may or may not have these transition rewards or action costs, right? So they are different. All these, the solutions to probabilistic planning problems are policies, but the characteristics that are decided in these policies vary according to all these different formulations. In particular, the kind of problem, the class of problem that we are trying to solve here, we call it high prob. And formally is this four tuple where V is the set of variables. We have the initial state as 0, the goal condition as star, and then we have this finite set of actions that have preconditions and stochastic effects. The solutions to high prob problems is a policy, and the quality of the policy, we measured it according to the probability of reaching the goal during execution. So we want to compute high quality policies. Now, why are we interested in this class of problems? Because there's really a limited number of solvers that solve these high prob problems. For example, we have this offline solver, that is Fred, in reality is a framework, that has optimality guarantees. But on the other hand, this is not really the fastest or the most efficient method. The one that is the state-of-the-art was RobustFF, RFF, which is an online planner, a replanner, that scales better and in practice has these better, higher quality solutions. But what happens on the other hand is that it has very limited optimality guarantees because it's only optimal when the problem has no dead ends. So, our objective is to develop this fast and scalable high prob planner that is offline and use, well, what will happen, and this is a spoiler, we'll have an improved guarantees with respect to the previous state of the art. We will do it by leveraging technology in fully observable, non-deterministic planning problems, and we will develop this planner that we call PROPRP that outperforms the previous state of the art. So, why do we leverage font planning technology? There's two good reasons to do that. The first reason is that the model for font planning and the model for probabilistic planning, they are very similar. And they only vary in this red line where the effects in the probabilistic planning problems are stochastic and here are non-deterministic. The second reason is that there has been very recent and huge advances in font planning technology that we can leverage. So in particular, we will extend the state-of-the-art font planner, PRP, into PROPRP, that is a high probabilistic planner. So let's look into the algorithm. there's 3 basic steps. In step 1, we determinize the problem, we take the all outcomes determinization, and we find a deterministic plan from the initial state to the goal. In this case, the plan is A1, A2, A3, with the effects that generate the states S1, S2, and the goal. Right? Second step. The second step, we select one of the states that are generated by the non-determinism of the actions, in this example S3, and then we compute a deterministic plan for S3 to the goal or to a previously resolved state. And then, last step, we repeat step number 2 until convergence of the algorithm. That's the basic algorithm. Now, there are 2 very important improvements to this algorithm that help outperform the previous one. So, the first feature is this partial state representation, and I will tell you. So whenever we generate this deterministic plan, we can regress it to compute the relevant part of the states that is relevant to reach and necessary to reach the goal. This allows for a compact representation of the states that ultimately benefits the algorithm and speeds up the convergence. And we generate more compact policies. So, the second feature is this forbidden state action pairs. And the rationale is, well, whenever we reach a dead end, we can apply regression and compute this partial state action pair that recognizably leads to a dead end. And we can, from now on, forbid this state action pair from future searches. So, we present 4 different enhancements exclusive to PropPRP that leverage the probabilistic information and improves the quality of the solutions found. The first of the enhancement is a bias towards the search of high likelihood plans, where the likelihood of a plan is defined as the product of the transitions of the action effects that generate this plan. So when we generate plans that have high likelihood, this is beneficial, and we obtain high quality policies in those problems where the high quality solutions have plans such that the most likely plans are short and have transitions with high probability. And this, that is very difficult to parse, you need to trust me, it happens in practice. So, the second of the enhancements is the full exploration in the last iteration. And the rationale is that the forbidden state action pairs are very, very restrictive. So whenever we reach this forbidden state action pair, we prune this direction from search because we know that there's a non-zero probability of reaching the goal. But that's too restrictive because on the other hand, we may still have a non-zero probability of reaching the goal instead of a dead end. So what we do is we run this PropPRP algorithm, and when we converge, we run a final round, this time with the dead end avoidance disabled. This way, we can explore these branches of the policy that were quoted from the previous search and hopefully reach the goal with increased probability. The third of the enhancements is the early dead end detection. And the idea is that instead of detecting a dead end in the time of processing a state, we detect the dead end whenever we find these deterministic plans by exploring all these non-deterministic children of the states. And the fourth enhancement is what we call a safety belt. And the idea of the safety belt is to gradually disable one feature when it's detected not to be beneficial in the search. By doing this, we speed up the algorithm up to 2 orders of magnitude in the most beneficial cases. Now, the theoretical results, our algorithm ProbPRP is sound and complete, and it's also optimal in problems that have no dead ends or the dead ends are avoidable. This is already a step further with respect to the previous state of the art that was only optimal when there were no dead ends. So, experimental results. We like to thank Florent Teitail and Andrei Kolobov for the useful insights about how to perform fair experiments here, because we are comparing ProbPRP, which is an offline planner, with RobustFF, that is an online replanner. So, useful things here. We configured both planners with the best configuration, each one of these. Useful typical benchmarks, the triangle tire wall, box wall, exploding block wall, and schedule. And first thing, we measure the quality of the solutions. The quality is the probability of reaching the dead end, reaching the goal state during execution. In these domains, triangle tire wall, blocks wall, and box wall, both planners were found optimal solutions. The challenge comes in the exploding blocks wall and schedule problems, where here, well, we see that the quality of the plans on the y-axis is in general better for ProbPRP, with the exception of the largest instances in the schedule domain. For these problems, we limited the core search time of ProbPRP to 5 seconds, and after these 5 seconds, we performed this extra final round with the dead end disabled. The result is that the quality of the plans generated now are much better than the plans generated by RobustFF. Now we compare the planner runtimes. Top of the line is better for ProbPRP. In general, we are better. We highlight that in the triangle tire wall, which is the yellow one, we are exponentially better in runtimes. This is policy size. We see a general trend. Again, top of the line is better for ProbPRP. Again, for the triangle tire wall, we are generating policies exponentially smaller, and this is thanks to the compact state representation of ProbPRP. And, well, we are better, but what happens with the average plan length? Well, they are similar, so we are generating smaller policies, faster, and the quality of the plans, the expected plan length is still good. Now, we performed extra experiments to investigate what happens when we vary the probabilities and the action orderings in the problems. So the first thing we did was to take the triangle tire wall problems and modify the probability of having a flat tire after moving from 0.5 to 0.45. And then we asked planners to generate policies. So before, with the original probabilities, RobustFF generated 100% optimal policies. Now, the quality of the policies dropped to 5% in the third instance, showing that there are algorithms that are really sensitive to these probability distributions, whereas ProbPRP is optimal and has optimality warranties in these kind of problems with avoidable dead ends. The second experiment, we switched the order of the effects of the action, non-deterministic action move, so that now the first effect in the PDDL is the one that has the effect non-flat tire. Again, similar results. RobustFF, the quality of the policies of the instance number 3 dropped from 100% to 0%, whereas ProbPRP is still optimal. So, conclusions. We highlighted and exploited the similarities between the font and probabilistic planning models, and introduced the ProbPRP algorithm, which outperforms the previous state-of-the-art, has better performance and scalability, whereas it is offline, which is always a nice property. For future work, we leave to investigate the anytime behavior of the algorithm and to improve the probability reasoning. So thank you very much. And if you have questions, I'm happy to answer.
Thanks for the great talk. Any questions?
Not sure if it's a fair question. A few years back, I did some work on hybridized planning, where the non-deterministic planning and stochastic planning were combined to create a hybrid policy, and we also showed anytime behavior. Have you seen this paper? Have you been able
I've
to
gone
think
through
about
this
the
paper. I
differences?
know their existence. I'm not an expert in this paper, but it's very interesting. So I think that there are different kind of problems, like non-deterministic font problems, stochastic, shortest path. In fact, Florent has a paper that combines these stochastic. Sorry, I don't know how to stop with this. Okay. So it seems to work now. It's very interesting. Florent has also a paper where it combines the stochastic shortest path with what he calls stochastic and safest shortest path. So it tries to minimize the expected Planck length and then maximize the probability of reaching the goal. So definitely, there are so many problems that are similar in the core, and it's very interesting to try to generalize and see what happens. Yeah.
I'll still suggest you have a look at that paper because it has the same key idea of combining non-deterministic planning with stochastic planning. So it's the same general idea of using two planners, one which is stochastic and one which is non-deterministic.
Thank you.
Other question?
So, what if I wanted to change the objective slightly, and I wanted to find a policy which achieves the goal with at least 90% probability, right?
Yes.
But is the most efficient one from those, right?
What do you mean by most efficient?
In terms of cost, so average cost.
Okay, so action costs 1, right? So in that sense, our algorithm will not be optimal, but in practice, we have seen that the expected Planck length is very good. So we've had 2 experiments, one with this PROPRP version that I have explained here, and another one where we don't bias towards high likelihood plans. So biasing towards high likelihood plans can shorten the expected Planck length by orders of magnitude, like up to 3 orders of magnitude, more than 2 definitely in the most beneficial cases. But again, we are not optimal.
For example, in triangle tire if it's say 90%, then you can take, a shortcut right at the top.
Exactly. Yes. Yes. So our algorithm right now doesn't solve the at least problems, but I imagine ways to do that, like having a counter that counts how many probability have you left. Yeah, it's very interesting. Future work.
Okay, thank you. I had plenty of questions. I asked you at the break. You have to move on. Thanks. So now the third talk is the one which is switched with the other session. So yeah, for people who wanted to attend the robustest planning talk, you should go to the other session. So we welcome so Zachary Rubinstein. We will speak about robust allocation of array device capacity for distributed spectrum functions. And it is a journal paper.
Okay, great. So this is work on analysis of radio frequency devices, and we're trying to allocate radio frequency devices to do spectrum management, spectrum analysis. This is work that was done with Steve Smith and myself, David Shore from ACS, and John Chapin from DARPA. No, that was not the right button. There we go. Okay, so in a more general context of this, the idea is that you have devices that are out there for other purposes, like cell phones or radio devices. They're out in the world, and they're doing primary missions that are supporting things like communication, voice communication. And you're trying to say, in their spare cycles, can I task them to do some spectrum analysis functions. And so what DARPA wanted to do here is basically develop a OS system that was a distributed OS that would allow applications to then task these devices in their spare cycles to do some kind of radio frequency analysis function. So some of the sources of uncertainty that come with doing this is that these devices are mobile, and a lot of these radio frequency functions are dependent upon location. So as they move, you don't know where they are, so you have to watch that as you task them, because you can task them inappropriately if they're in the wrong positions. Also, one of the key points here is that the primary missions, like the voice communication support, may take over, and they always have priority over whatever these sub-analysis functions might be, because they're in spare cycles. So as a result of that, the idea is, again, to task these things given this uncertainty. So what's a good method and approach for doing this? So again, as I was saying to you, the DARPA concept here is that you're going to have this sort of distributed OS that's sitting on top of it. Exactly where it lives, it's either on the devices themselves or some servers that live out there. And then you're going to task these devices through this thing. And this OS is going to support a tasking scheduling service for figuring out which locations to do these things. And so to make it a little bit more real, well, let me first talk about what our objective here is. Our objective here is to perform and provide this kind of tasking capability within this OS system. The approach that we've used is a decentralized market-based approach. It has some advantages in that you don't have to centralize any of the state information. Each of the individual devices will know where they are, so when they send in their bids, they will be able to tell you their location, rather than trying to keep an updated, maintained state in some centralized place. The second thing we're going to do is that in determining which things to task, we're going to use a constraint-based search technique to review those bids and determine which bids are the appropriate ones to allocate to any particular task. And finally, I'll talk a little bit more about this probabilistic post-analysis. And the idea here is doing targeted additional allocation of radios to a particular task to increase the probability that they will successfully coverage, or at least that they proportionally will be more successful. And I'll show a little bit more details on that. To give you a little bit more real fast example here, here's sort of downtown Pittsburgh. You can see sort of like these cell phone icons that talk about these radios. The idea here is that they would receive some job from some application through this OS system. They would send out bids that have particular requirements for the announcement. I'm not sending out bids, send out the announcement. And then each one would formulate, based on those requirements that came with the announcement, their bids and whether they could achieve them or not. Here's an example of the bids. And then they would send it back to the receiver of the request from the application. It's going to make a determination about which bids to assign and then send out the assignments. So this is not really a big subject of the talk, but I just want to give you some notion that every different kinds of tasks that you might be able to assign for this radio frequency analysis function may be complex. And so we're representing each type as a template, and the templates show different kinds of orderings. For the rest of the talk, I'm only going to talk about an atomic type of task, which I call scanning, or it's called scanning in the literature. All right, so for our method for determining which bids to assign, given that we give them back, we're using the min-set cover heuristic. And basically what this is saying is that if you have a first scanning task, you have a region that you're being requested, and in that region that you're being requested, the idea is to get nodes that overlap with that region so that you can maximize the coverage over the entire region. So really, very simply, all the min heuristic says is that you go through it, and the first time around you say, oh, which node overlaps the most? Allocate that one. Keep iterating until there are either no more bids, or actually until the region is covered, or there are no more bids. And so some of the nice properties of this min-set coverage heuristic is that it achieves the best approximation bound for this task. It is a greedy, efficient allocation, so it's very fast. And what I didn't mention is that this has to be done in milliseconds. Typically, you have maybe small windows that you're allocating over, which is like 10 seconds horizons, and then you have to make these decisions in milliseconds. And so it's really not going to be appropriate to do something that's very exhaustive in search, but you still want to get a good result. Finally, as I was saying, that we're using coverage in this particular example of the spatial coverage on the request versus the how much the nodes can cover that request region. All right, so that helps you a little bit, as I told you with the auctions, helps you a little bit with the location uncertainty because each node knows its own device, its own location when it sends in the bid. But what you don't know is there any other kind of information out there that can help you with that uncertainty? In particular, is there anything information that can help you with, hey, is that primary emission going to kick in and not make it possible for me to have that node successfully handle it? So what we were told, and it seems that it could come from historical information or even first principles about the knowledge of the usage of how that device is going to be done, is that each node can sort of tell you in the next period of time the probability that it's going to be available. We represent it as a sort of a step function over the horizon that shows you the probability that it will be available. They said likelihood is it's just going to be one number. So for the rest of the talk, I'm just going to talk about it as though it's just a straight line across for that horizon for each node. And so in practice, as I said, there will only be single probability. What we've decided is now, how can we incorporate this information, again, to reduce the uncertainty? And basically what we did is add this extra term to this additional coverage. So now we're doing coverage not just by the proportionality of the region being covered, but also by what's the probability that it's going to be available. And we just added that term to it. So as we took this new bias allocation, and now we're going to do some evaluation on this to see how well it performed. Before we do that, let me just talk about some of the evaluation we did here. This is just the experimental model, basically the experiment design. We have the 6,400 by 6,400 meter grid, which represents the entire scenario space. Inside that, you can randomly generate locations for nodes, and you can randomly generate locations for requests. Requests can have different size regions. Nodes can have different powers in different spaces, and they can cover different amounts. All right? For each scenario, for each dimension, you'll see what we do in our experiments is we're going to fix everything and only vary one dimension. We do 10 scenarios for each one of those. So on the evaluation, what we do is that we're going to generate a scenario. For each scenario, we have the set of allocated requests in the scenario. We're going to evaluate the score, which is really the coverage, which is just the actual coverage over the requested coverage. So obviously, 1 would be a complete coverage. Anything less is not quite coverage. Partial coverage is okay. We have this particular unique thing we're doing with priority scoring, which we're just using in one example, and I'll show you that. But basically all it's saying is that we're going to, in lieu of having real bumping and preemption of requests and resources, we're allowing to evaluate priority requests by basically giving score higher to the earlier request than the later request. And finally, the executions of each task are simulated by, you take the lowest probability, of course, when there's only one probability, it's always the same, for the scheduled execution interval, and then sample that. And we're going to do this 100 times, a simulation, take the average, and that will give you the score for the scenario. A perfect score is obviously going to would be 1 for each request, so the number of requests would be a perfect score. 5 minutes. Okay, great. All right, so very quickly here, we did a single mapping request here, which means one big region where we have one request that says map this whole request, and then we have a bunch of nodes on it. So, well, that's nice. We get font mess ups here. So anyhow, the piece here, the ideal here, just to give you the big picture here, is that as we increase the number of nodes, the biased one, which is the top line, is doing much better than the unbiased one. So the availability does seem to have the effect that we want. Also, as you would expect, more nodes are allocated on the biased ones, on the early ones, but as you're going across and adding more nodes, it becomes less, and that's basically because you have more nodes, so you have better selectability, and it's more likely that the probability that you're going to find good nodes, so you don't have to allocate additional nodes. Oh, let me go on. So we did the same thing then with multiple requests. And so we fixed the number of request devices at 25. We have a dividing radius, just the size of the nodes can scan. And then we vary the number of requests, each targeting from 200 to 800 meters. And then as we see the number of requests, as you might expect, again, the bias is much better than naive, where it starts to fail down is when you get oversubscribed. 200 requests, doesn't matter. There's not much allocation decisions you can make at that point. Again here, we did that prioritized scoring, and we've seen the same kind of decline, although it's a little bit less, suggesting that the earlier, more high-valued requests got better value. Again here, we did increase capacity of nodes. As we saw in the single case, the single mapping case, it's very much the same kind of trends, we saw this doing much, the bias doing much better as you got more, and as you have more capacity nodes, and the number of nodes that you have to allocate per request converges to the same thing as naive because you have more selective pieces to choose from. Real quickly then, so, wow, very different colors than my slide, sorry. So the ideal here is that we then wanted to do this targeted redundancy, which allows us to say, hey, some requests are more important than others. We want to add some additional probability that these things are going to be successfully executed. And so what we did is basically kind of form this heat map here where we looked at the overlapping coverages of the nodes and we say, here's the probabilities of those things. We added them up and say, where are the weaknesses? Where are spots of it? And then we take the additional bits that might be remaining and say, can we add on to that and then increase those probabilities? We have two control factors here, which are, one is the n, say the n top one, say, give me the n weakest regions and let me reinforce those. The other one is, say, a threshold, and say anything below that threshold, reinforce it until the threshold, you're above that threshold. So really quickly here, 2 minutes, great. All right, so really quickly here, what we saw is that very early on in a single mapping request thing, you saw that the benefit of the n highest ones, you got the most benefits in the very early on ones. So the very early ones, you got the best benefit. One thing I wanted to show you also is that we did optimal, and all optimal means here is you allocate all the requests, and therefore you would get the optimal score because it's a single mapping request. I mean all the nodes, I'm sorry. And then you see that very much the bias got very much the same as the optimal with far fewer nodes. We then did, again, the request over here with multiple requests. And we saw here that basically what happens is in this kind of scorings here is that we segmented the requests into different classes of requests such that the thresholds were higher. So critical had 0.8, the non-critical were 0.5, and the optional were 0. And as a result of this, you could see that we actually got better value. And more importantly, what we saw is that actually the critical ones were much higher coverage than the non-critical. So you really got the effect that we wanted to get. We compared to optimal, I know it's about a minute. So in optical, we also then created MILP solvers to compare against optimal. We saw very much the same kind of trends we saw earlier. Of course, the optimal did better. It's solving a different problem. What the optimal is solving is it knows all the requests in advance. So it's solving it all in advance. It's not trying to reserve resources for later requests. So it's a little bit different. So it's not even a realistic line, but still you can see that we got this optimal result. The bottom graph, what it shows here is most importantly is that the MILP solver is really not very functional for this thing. It does it in terms of minutes. It actually couldn't solve some of the bigger problems. So again, this is just showing that the nodes required. We also did a MILP solver that said the number of nodes that you needed to do to use to achieve the result that each individual heuristic solver solved for each request was less. But it's not a whole lot less, and that was also a good result. So finally, in future work, we have different directions that we're going. One of them is 3D coverage. Everything I just spoke about today was about spatial coverage. But as you can imagine, they also have, say, hey, we want to monitor particular frequencies, particular bands. And as a result of that, we're also doing this kind of, instead of changing from spatial to a volume-oriented model. And also a reactive reallocation. One of the great advantages of the auction is that if you do fail, you can rebid it. You can resend the auction out. And as you can see, failure is a high probability here on different devices. So we didn't work in that kind of mechanism. Multiplexing of devices, we acted as though these are monolithically atomic devices that can only do one thing or the other, but in reality, many radios can do multiplexing, and so you have to do finer grain allocation. And finally, node usage dependencies. Just because one node, we're modeling availability of nodes independently, and the reality is that a lot of times groups of nodes are set off in use, and so you'd like to be able to leverage those uses of clusters of nodes. Thank you. If anybody has any questions.
I think we have time for one question.
Sorry, this is slightly open-ended, but looking at this problem space, it looks remarkably similar to me to the Uber problem.
Okay.
So the sense of here's a bunch of tasks and requests coming in, and this sort of bid mechanism of who's going to get allocated to which task. I guess can you comment on a little bit if there's extensions here that apply to that problem or vice versa? I guess in that problem it's more taking people from one destination to another. This is a little more trying to establish coverage of a total area.
Right.
I just didn't know if there was any sort of connection between work that goes on in that space.
I can imagine the Uber problem being done with a market-based approach. So it's similar in that sense, that you're going to do task allocations. A lot of the Uber one is you're going to do these kind of vehicle with time windows in some sense. Basically, you're going to have to figure out the distance, the setup cost, which is the distance any particular driver is going to have to go to that piece here. Here, we don't have those kind of setup costs. So it's a little bit different in that sense. This thing also, the horizon is short, but again, you're right. They're very similar. Still a task allocation problem. So it doesn't differ a great deal in that sense. The approach, I think, you can still apply. But again, I'm not saying that we started market-based approach. That certainly has been done preceded for us.
Okay, let's have the speaker again. And now the last talk of the session is a long paper presented by Javier Segovia about generalized planning with procedural domain control knowledge.
Does it work? Yep, it's here. It's great. Fine. Okay, so I'm Javier Segovia, and I'm going to present a joint work with Sergio Jimenez and Anders Johnsons. So we start from the setting of classical planning. Imagine that we have a domain where we want to sort a list of numbers. And a classical planner will produce a sequence of actions. So in the end, we have this list of numbers sorted. So the one action that we find in the classical planner is to swap the values 2 and 1 here. So we select these two values, we swap them, and then we take the values 5 and 2, we swap them, so we get the sorted list. Okay? But what happened? That this is a solution for a specific problem. That if we provide more than one specific problem, and we want a solution to solve all of them with just one plan, we need a more complex structure, so a sequence of actions is no longer valid. Then what kind of structures can be useful to sort all these specific inputs? So we need a structure that allows branching and allows repetitions. So the kind of structure that we are working on is on planning programs. Okay, so in these planning programs, we need this branching. For example, for the case of the sorting domain, because we don't know which values can be in any of the possible positions of the list. And also we must allow repetitions because the list can vary in the size. So we need this kind of a structure to solve sorting. The contributions of our paper is that we implemented a call stack in PDDL. So now any classical planner can use procedures to solve more complex problems. This is generated automatically, so each procedure can call to any previous procedure and with any classical planner off the shelf. And also this is an ongoing work from an original compilation, and we reduced the number of conditional go-tos that are used for branchings and repetitions for creating these classical planning problems. So to introduce, we use classical planning that is just a set of fluents. It's a tuple with a set of fluents, a set of actions, an initial state, and a goal condition. And this will produce a sequence of actions that apply from an initial state, we satisfy a goal condition. So we extend this classical planning with conditional effects, because the actions that we are going to use in order to generalize are actions with conditional effects. So this classical planning uses literals with fluents that can be true or false, and the states are a set of literals. And these actions are applicable in the state if the preconditions holds in the state. Also, if the conditions of each one of the actions holds in the states, we'll produce a set of triggered effects that are literals. And the resulting state is just to subtract the negative triggered effects and then add the positive triggered effects. So in generalized planning, now we know that we use classical planning with conditional effects. So in generalized planning, what we use is a set of classical planning problems that shares the model. So all the fluents and actions are the same for each one of the classical planning problems. And the only thing that varies from one to the other are the initial state and the goal condition for each one of them. So we can say that the generalized plan solves the generalized planning task if it can solve each one of the classical planning problems of the set. This can be one example for a generalized planning task where we can have an initial position in any position of a grid, and we have to go to any arbitrary position in that grid. So the representation is given a classical planning problem. We want to produce a program to solve this. And this program is just a list of instructions. What are these instructions? These instructions can be sequential, that are actions in the original compilation. A conditional go-to, that is the go-tos that allow us to jump, to do branching or to do repetitions. So we evaluate a fluent. If a fluent is false, we jump to I prime. Otherwise, we go to the next line. And also, we have another instruction that is for the termination of the execution of the program. So this can be an example of a solution of a planning program. So we can be in any arbitrary position in a grid, and we want to go to the cell 0, 0. So the planning program to this problem is to decrease the x coordinate until I reach the x equals 0, and then decrease the y until the y is equals to 0. And then I finish my program. So if you want to have like an example of the execution of that program, I can take the same domain with just one instance as an example. So we are going to execute we are going to initialize the state of the problem with the coordinate 2, 2, and a program counter that is it's used to know which line I have to execute in my program. So I start from the first line, I decrease, then I ask, the conditional go-to says, it's x equals to 0? No. So I jump to line 0 again, I decrease it, I ask again, because now it's 0, I continue my execution in the next line. So now with the same happens with the y. It's a sequential instruction, then a conditional go-to, I go back, then I finish my execution. So the planning program solves the classical planning problem if it ends successfully, so that reaches the end termination instruction, and the goal condition holds in the final state. Also, this planning program solves the generalized planning task if it solves each one of the classical planning programs that compose this generalized planning task. So what about our compilation? Now we have the intuition of execution of our program. So the compilation, if we take a given classical planning problem, we produce another classical planning problem, but we have to specify this bound that are the number of lines that our program must program, because our search of our classical planning of our classical planner is exponential in this factor. So it's important to specify this bound. This one also will affect to the rest of the tuple of the classical planning task. So we extend the number of fluents with all the program counters that are the fluents required to know which line I can execute in my program, and all the possible instructions that I can have in my program. So all the possible instructions that I can really program in each one of the lines. What are these instructions? The previously explained. So are the original actions of the domain, the conditional go-tos, all the possible conditional go-tos, the termination instruction for each one of the lines, and the new instructions that are to say that we have empty lines that must be programmed to finish our program. Also, the actions, the original actions, are split into two ways. One for them are programming actions, the other ones are repeated actions. So the programming actions has the preconditions of the original actions, and also we have to, the program counter specifies which line we are trying to program, and this line must be empty. If this line is not empty, I cannot program this line because it's already programmed. And if a line is already programmed, then I can repeat the instruction that is programmed in that line. And the execution logic is previously explained in the example. The initial state, we take the initial state of the original classical planning task. Also, we add the program counter to 0, explaining that we start from the first line, the execution, and all the lines of the problem are empty. So our program is empty, we must program it. And the goal condition is the original goal condition, adding the fluent done, that means that we have ended successfully our execution. So now that we have a compilation for one of the problems, now we can create a generalized planning problem. How is this generalized planning problem? It's a set of classical planning tasks. So this extends the previously explained with the test fluence. That means that we are executing a specific classical planning problem. And we move to the next one when we solve one of them sequentially. In the actions, we have to add it because we have now more than one classical planning task. We have to add more repetitions for determination instructions. Where each one of these termination instructions, the goal condition of each one of the classical planning tasks must hold in the state. So if one of these goal conditions holds in the state, I set my program counter to 0 and I move my state to the next initial state, that is the initial state of the next classical planning task that I want to solve. But if it's the last test case, the only thing that I do is to set the fluent done. And the initial state in the generalized planning problem is the initial state of the first classical planning task that I want to solve, with the program counter 0 and all the empty lines. And the goal condition is the last goal condition that I have to achieve with the fluent done. So now this is about background. So our contribution here is that we are implemented from that compilation and extension with procedures and a stack. So the stack is the most important thing that we implemented, and it allows us to call to other procedures previously learned. So in this example, we have a grid where we have to visit the 4 corners of the grid. We can be in any arbitrary position. So we have a stack here, and the stack starts with stackable fluents that are the procedure we are executing and the line we are executing in that procedure. So we start in the main with the program counter 0. That means that we are in the procedure main and the first line to execute. So what's the first line of the execution? The procedure 1. The procedure 1 was previously explained in an example where from any arbitrary position we can go to the cell 0, 0. So we execute it, we make a call of that procedure that is already learned, and we move one position to the top of the stack, adding the procedure that we want to execute, and the program and the line that we want to execute on that procedure. So we start always from the 0 line of any of the procedures that we call. We execute. When we reach the end of the execution of the procedure, we move to the next line of the main. When we move to the next line of the main, we make another call to the second procedure, that is moving to the left, to the right part of the grid. When we finish, to the top, left, and we finish our execution in the 4th line of our main. So this is the intuition about how it works. Now about the compilation. The compilation is to take the previous compilation and we add 2 more bounds. One bound is to specify the stack size. So the stack size is what allows us to call other procedures. It's a bound to call other procedures, how many procedures we can call, also how many local variables we can set, and also which is the bound of a recursive solution if the planner finds something about the recursion. Also, we have to specify a bound with the number of auxiliary procedures, so procedures that we can call from our current procedure. That is very trivial. So we take the previously explained fluents, and now we replicate all these fluents for each one of the lines and each one of the procedures. Also, we have to include the top of the stack, because I have to know every time which line of the stack I'm executing, which is the top, so which is the current execution. Then the stackable fluents are the program counters, that is the line I'm executing in which part of the stack, and the procedure I'm executing in which part of the stack, that are like local variables. And then we have to include the calls from any line, from any procedure to any other procedure previously learned. So if I want to learn something new, it can use previously learned procedures. Then about the actions, is the same as the same that happens with the fluence. We take the actions of each one of the lines and we replicate them for each one of the procedures I can have. So now actions can have also programming calls and repeat calls. That is what allow us to call to other procedures. And now the actions also allow the instruction, the termination instruction, that it depends now also on the level of the stack we are executing. If we are not in the main part of the stack, in the 0 level, it means that we have to pop one of the procedures and the program counters of our stack and move to the bottom. If we are in the bottom, in the 0 level of the stack, it means that we are in the main. So if we reach a termination instruction, it means that we have finished our execution. So now the end, the repetition of ends has more logic than before. Also, the initial state is the previously initial state bounded with n, and we have to add now the program counter in the 0 line of the current procedure. We have to specify that we are in the current procedure, and the top is always 0 every time that we start a new generalized planning problem. And all the lines of the current procedure are empty because we have to program each one of the new procedures. So every time that we finish a generalized planning task and we have a solution with the planning program, we take this program and we introduce this knowledge as part of the initial state of the next procedure that I want to learn. And this is a process that is automatic because I have the solution of the plan, so I take this solution and I insert it in the initial state of the next one. So when we have all the nested procedures working, we can do an extra thing, that is, we have procedures and program counters as a stackable fluence. So like local variables that I can use in my stack. So now I can take, for example, some objects of binary tree search where are nodes. And these nodes can be included in as part of the stack as local variables. So when I include these objects as local variables, I can use it for recursion. So this is an example of a traversing binary tree. And the planner finds that using this node as a local variable, I can visit the current node of the tree. I can copy the left child of this current node in another variable that is called child. I check if the current node is internal or not. If it's internal, means that we have more tree to explore. If it's not internal, it means that it's a leaf. So we jump to the end. Otherwise, it means that it's internal, so we have to continue the exploration. So we copy the right child to the current variable. So we overwrite the current variable. Now we have in the child variable the left part of the tree, in the current variable the right part of the tree. So now we can do a call over the same procedure over itself. So it's a recursion over the current variable and then the child variable. So we explore the right part of the tree and then the left part of the tree, visiting each one of the nodes. And this is found by a classical planner. About the evaluation, we have to say that some of the domains were used from the benchmarks, and some others we have to create it like a sorting or the binary tree because they were not implemented for generalized planning. Also, we have to say that some of the domains can be solved without using procedure knowledge, but some others, like the grid domain, we need this procedure knowledge to solve it because it's impossible. There are a lot of lines, so it's exponential in the number of lines. It's quite hard. And the most interesting, maybe, were sorting and the binary tree search. That is like the first search solution found by the planner. So in conclusion, we may say that we created a novel compilation that can use procedural domain control knowledge and into PDDL and allows to call other procedures. So this is also in a nested way or in a recursive way, and it allows to solve a really complex tasks like sorting or a depth search. Also for discussion, we may say that the solutions are really compact and are readable, so human can interact with that solutions. If someone thinks that they can introduce some instructions in the program, it's pretty easy to modify it. But the solutions are not guaranteed or are not valid for any instance. we just guarantee that are valid for the instance that we provided to learn. So it's like in machine learning. And some domains require some high-level features in order to allow repetitions, like well placed in the top of or something like this, because otherwise it's impossible to generalize. And maybe the strongest assumption is that the task must allow some kind of subtask decomposition in order to decompose in different procedures. And as future works, we must say that we can learn some high-level features on the generalized plan. So instead of using the high-level features implemented in the classical planning task, we can search these features as a combination of fluence. That is a paper already accepted in ICAPS that will be presented next month. And also, we can explore some new ways about automatic subtask decomposition and identification of test cases that produce these effective generalized plans, because by now it's a human task. It's not something already in research that exists. So thank you. If you have any questions.
Thank you. Questions?
So I understand that you can't make any guarantees in general, but are there some conditions where you can guarantee that everything works, like if there are, if all actions are reversible or something like that?
We cannot. It's like in machine learning. It's the same machine learning problem. You provide a training set, so you know that you are working for the training set. Maybe for some other test set, it's not working. You don't know.
Yeah. So maybe like a pack guarantee or something, right?
Maybe. I don't know.
Thanks.
So I think there's a really cute work. It seems to be identifying a very nice fragment of program synthesis, right? I mean, sort of one that can actually be compiled into a planning problem. So in that context, my main question really is, so first, which applications do you think have that profile where you can apply this? And second, as you know, there's a, synthesis is an age-old problem that has been considered widely. So how does your work relate to that? And could you potentially sell your work to that community? And that's something I'd really like to see.
Split maybe the first question. What was the first question, sorry?
Well, the first one is, which applications do you think have the profile where you can actually apply this? Like, where would it be useful? And second, synthesis is a really big research area, and how do you place yourself in that area?
It can be really useful to get some compact solutions for problems that are complex. I mean, it's a very intuitive way it's a very intuitive framework to interact with humans. So if someone knows that some conditions must be placed in some specific part of a program, I can place these conditions as a part of the initial state, and I can load my classical planner to search for the rest of the program. So I think it's like a milestone, maybe, to automatic process of complete full automatic programming.
How is actually using this as a high-level abstraction for routing problems? So we're going to analyze programs for top level, selecting one example of
Well, it can be used for anything that can use a controller.
But synthesis, I'm not so sure that we're at a level yet that we would compete with.
I don't know. I mean, synthesis is like way too hard to be solved. So it seems to be an interesting fragment. All I'm asking is, what is the concrete? I mean, robot programming is one case, I guess. And then put to place it in the synthesis literature. I mean, could they actually sell this to the synthesis guy?
We're still kind of getting familiar with that literature. I'm not sure. I feel that we probably have some way to go. It's a possibility.
Yeah, I was wondering, how does the size of the stack and the number of procedures impact the complexity? How does the size of the stack and the number of procedures, which are parameters of your algorithm, how does it impact the complexity of the
We're talking about the bounds of the programs?
Yeah.
So here are more or less the ones that we use. Maybe the more
Okay.
more complex bound, but the more complex bound is the lines that the search is exponential in that bound. Maybe the procedures are just something that we must place in order to create the correct fluence to the calls. So it's very trivial. The bound of the procedures is not something bad, and the stack is also that doesn't affect too much. because if the planner doesn't search a recursive solution, it won't use the stack. So the number of lines is the most critical part of the.
So one of the things that would be nice is if you have one of these compiled generalized plans, there's some sort of wrapper information, such as like preconditions and postconditions, so that the planner can say, here's an already compiled, generalized plan that I can use as an action. Do you have any of this sort of wrapper information?
No.
Sort of like in HTM.
Yeah, but we don't use this partial order of the task as an STN. So maybe some procedures maybe that we learn are independent and maybe are not useful to learn new procedures. I don't know.
I think we partially do that. The initial state is flexible. You can put in an action as part of it, an instruction as part of the initial state, or you can leave it blank and add the standard of programming. Put in as much initial knowledge as you have.
Yeah, for that reason, depending on the previous knowledge learned, it can be useful to learn a new procedure, or maybe it's not useful. So maybe they are independent as well. I don't know.
Any other question? No. So it's time for a coffee break. Let's take again.